Okay, hello everyone, and welcome back to your YouTube channel. And today we have a very simple and practical session, but it's extremely helpful. Um, Today I prepared this practical session that is related with power system analysis. Specifically, we are working today with asymmetrical short circuits. And the objective of this video is to show you some practical calculations related to the use of symmetrical components for short circuit calculations, specifically related with asymmetrical faults. Um, let's start with this session, and there is a very basic problem here. Okay, we have a power plant, and this power plant has 4 generation units. There are 4 generation units in the power plant, but the schematic diagram of one of the generators and transformer units are shown below. Okay, this is the single line diagram for one of the generators and transformer set. And as you can see here, we have a synchronous generator, 75 MVA and 11.8 kilovolts. And here we have the data for positive, negative, and zero sequence, positive, negative, and zero sequence, okay? And then we have a step up transformer, 11.8 to 66 kV, and this is a three-phase 75 MVA transformer, and the reactance of this transformer is 10%. The interesting thing here is this is a delta star connected transformer, but there is an impedance, in this case is a 38 ohms resistance that is connecting the neutral point of this star to the grounding system. Okay, well, the first thing that you need to know is that this generator transformer unit, these elements, they are not connected to the rest of the power system. What I'm trying to say is they are isolated and working on known load conditions, okay? Known load conditions. That means that the current here is 0, and the voltage at the high voltage size of the transformer here, it's 70 kV, 70 kV line to line. Well, suddenly we have a short circuit at the high voltage terminals of this transformer, specifically here at this point F, and we want to calculate the short circuit currents, of course A, B, and C, in amps, real units, amps, and assuming that they are a fault, okay? And the first question is related with a three-phase fault. And over here, you can see the results, okay? And the second question is related with a line-to-line fault, line-to-line fault. And finally, we have here the single line to ground fault, okay? What I'm trying to say is we are solving three different and three very important questions in this problem. The first one is three-phase short circuits. I know three-phase short circuits, they are symmetrical faults, but the idea is that you must understand how to use symmetrical components in order to perform calculations in electrical power systems. And then we have a line-to-line ground, a line-to-line fault, and finally a single line to ground, okay? Well, there is a very important information here, something that you must be aware. We are requested to use a specific base for the per unit calculations. In this case, the apparent power base is 100 MVA, and the voltage base is 66 kV at the high voltage side of the transformer. Okay, this is just a specific request in order to get the proper per unit values. Okay, well, it's time to solve this very interesting question. Okay, what is the first step? The first step is extremely simple, because what we need to do is transform or convert all the per unit values into the common bases that we are asked for. What I'm trying to tell you is, in this problem, we are using 100 MVA as the apparent power base for this problem, and also 66 kV at the transmission level. That means the high voltage side of the transformer as a common base values for the per unit calculations. That means that those per unit values here, sorry, this is zero sequence, those per unit values must be converted, must be transformed into the new base system. However, all my students, they are extremely clever, and they must remember this amazing equation over here. And this equation is used to convert per unit values from one base to another base, okay? In this case, we call all base the specific base that they are coming from the nameplate or the data that we were given. And the new base, they refer to the bases that they are asking for to use, okay? Let's start with the generator, okay? The generator has three different reactants, because we have positive, negative, and zero sequence. And what we need to do is we need to use this equation for the positive, negative, and zero sequence, but keep in mind that the voltage base is the same, 11.8 kV, but we need to change the apparent power. 75 MVA is the old base, and we need to transform to the new one that is 100 MVA. Well, as you can see, the calculations, they are extremely simple, extremely simple. What you need to use is your basic calculator, or if you prefer, you can use MATLAB or any other kind of programming, Python, whatever, and you can get the positive, negative, and zero sequence for the generator. Similar situation must happen for the case of the transformer. However, the good news is, in this case, we are using a three-phase transformer, and positive, negative, and zero sequence reactance for this transformer, all of them are the same. That is 0.1 per unit. And we don't need to change voltage base because all of them 66, but we need to convert the base from 75, that is the nominal power of this transformer, into 100 MVA, and that is the new base that we are using, okay? Again, a very simple equation. You put over there the numbers. You can use a calculator, or again, you can use any kind of software. For instance, you can use Python or MATLAB, okay? And you get the result. Now, the next step is, all of you must remember that in this case, we have a resistance 38 ohms, and these 38 ohms, they are connected between the neutral point from the transformer neutral point, the star neutral point on the high voltage side, to the grounding or earth system. Now, what you must remember is that for zero sequence current circulations, the impedance that we need to use is three times the real resistance that is connected between the ground and the neutral point, okay? If you are confused about the reason behind the three, you can go into my classes and you can see the proper, the formal deduction of this demonstration for this number three. But specifically, this three is to represent the zero sequence flow, current flow through the neutral point, okay? Well, 3 times 38 ohms, that is 140 ohms. However, we cannot use directly the 114 ohms directly because we are using per unit values. As a consequence, we need to convert these 114 ohms into per unit system. And the best way to do that is dividing the real value, 114 ohms, by the impedance base, okay? However, one intermediate point that I need is the current base. And to calculate the current base is extremely simple. All my students, they are familiar with the three-phase properties, and there is a very important three-phase property related with power. And all of you must remember that if you divide the three-phase power by a square root 3 line-to-line voltage, we will obtain current. What I'm trying to explain is that the base current is the base apparent power divided by square root 3 times the line-to-line voltage base, and that is 100 MVA divided by square root 3 times 66 kV. Now, what you will get is the base current. And as you can see over here, the final base current is 874 amps. As you can see over here, I always suggest my students to include this small remark here at the very end in order that they realize, they understand, and they remember, especially they remember, that this is the base current at 66 kV or the high voltage side of the transformer, okay? Well, we know now we know the base current, and the next step is I will calculate the line to neutral voltage, okay? The line to neutral voltage, again, my students, they are extremely clever in terms of circuit analysis. And again, there is a three-phase property. And these three-phase properties say that the line to neutral voltage is equal to the line-to-line voltage divided by square root 3, okay? Remember, this is the magnitude, the line to neutral voltage is equal to the magnitude of the line to line divided by square root 3. What I'm trying to tell you is this is the magnitude. Probably you are wondering why this gentleman is saying that. Because if you are applying the proper three-phase property, you must remember that there is a 30-degree phase angle involved in the full equation. However, here, I just care about the magnitude, and the magnitude is extremely simple. 66 kV divided by square root 3, and we get 38.1 kV. From there, now we know the current base, and also we know the impedance base, because the impedance base will be the division. You must remember this equation. This is Ohm's law, and Ohm's law say that the impedance base is the voltage base divided by the current base. In this case, 38.1 kV divided by 874 amps, And we get here an impedance base that is 43.56 amps, okay? I forgot to include here, but I will do it using my handwriting. And this impedance base is for 66 kV. This is a very important remark, okay? This remark, this small notation over there, it will help you in the future in order to avoid mistakes in your calculations, because now you are totally sure that this is the impedance base for this very specific voltage level, okay? My clever students, they must remember that there is another way to calculate the impedance base. If you want a shortcut, you can say that the impedance base is the voltage 66 kV divided by 100 MVA, and you will get the same number, 43.56 amps at 66 kV. Okay? What is the idea, my students? If you want to use this equation, it's perfectly fine. It's perfectly fine. But remember, you will need also the current base, because in this problem, we are calculating currents and we are asking for amps. And fully know and understand the amps, okay? What is the next step? Okay, the next step is now we know the impedance base. And if we know the impedance base, we can calculate the zero sequence impedance, remember, for the earthing or grounding resistor. And that is using just the basic, this is the basic definition. The zero sequence impedance in per unit is equal to the impedance in ohms divided by the base, and we divide 114 ohms resistance by the impedance base, 43.56, and we get this number here, this beautiful number over here, 2.61 per unit, and that is the resistance in per unit, okay? Well, next step, we need to know what is the per unit value of the pre-fault voltage. What I'm telling you is, in this case, the system is working at a steady state condition previous to the fault. And in this case, we know that the voltage is 70 kV. 70 kV, 70 kV is the steady state voltage previous to the fault. And we need to know that voltage in per unit. And that is very simple. We divide 70 kV line-to-line voltage by the base, and that is 66 kV, and we obtain 1.06 per unit, and that is the voltage that we call the pre-fault voltage. Well, now we are ready, because that is a very important step. The very important next step is to create, we need to create the proper positive, negative, and zero sequence, okay? Networks. We need to know, we need to be sure that we know the positive, negative, and zero sequence networks, okay? Positive, negative, and zero sequence network. For the positive sequence, it's extremely simple. For the positive sequence, we have here, this is the positive sequence from the generator, and this is the transformer reactance, okay? Extremely simple. Internal voltage, this is the generator positive sequence reactance. This is the model for the positive sequence of the generator. And here we have the series reactance of the step-up transformer. Very simple. Then we have the negative sequence. You must remember negative sequence, they are not voltage sources. They are not voltage sources of negative sequence because the synchronous generators, they are the only devices, active devices producing signals, and all of them are positive sequence. Negative sequence, they are not voltage sources, but here we have the negative sequence. This is the negative sequence reactance of the generator, and this is the reactance for the transformer. Very simple. And finally, we have the zero sequence network, and the zero sequence network is probably the most interesting one. The zero sequence is the most important one and the most interesting. You must remember this is the zero sequence, reactance of the generator, but here we need to use the model of this very interesting transformer. If you remember, we are using a two-winding transformer. This is a two-winding transformer. This is the low voltage side. This is the high voltage side. And the connection, the vector group here is delta to star. And there is a neutral resistance and neutral reactance, okay, neutral impedance. If you remember from my classes, from my documents, you must remember that when we have the delta connection, this is the low voltage side, yes? There is not possibility for zero sequence currents to move on the lines because the delta connection stops the zero sequence circulation. But on the star connection, we have here the reactance of the transformer, and this is the high voltage side. But when the zero sequence currents arrive to the neutral point, they go to ground through the 3 times zero sequence impedance, neutral impedance. And this is the model that I am showing here. This is the transformer. And here we have 3 times the neutral impedance or zero sequence neutral impedance, okay? Extremely simple. All my students, all of them, I am sure that they can remember this and they know the proper theory behind this, okay? I am sure of that. What is the next step? I need to simplify these circuits, okay? This is positive sequence network, this is negative sequence network, and this is zero sequence network. But here we have a series connection, two impedances, series connection. Here we have two impedances, series connection. And I believe all of you can see this is the zero sequence connection, and there are two impedances here in series connection. We can apply the Thevenin theorem. We can solve the series connection, and that is extremely simple. All my students, they can do that. And this is the Thevenin impedance for the positive sequence, negative sequence, and zero sequence, okay? Something that is very simple to see is we have here a reactance, zero sequence reactance 0.133, that is here. And the neutral point, you must remember this transformer has a resistor connecting the neutral point to the ground. And you must remember that value is 2.617, and that is the real part of this Thevenin zero sequence equivalent because this is the resistance, okay? Well, this is a very important step forward because now we can have the three very important sequence model, okay? We have the positive sequence, we have the negative sequence, and the zero sequence network. In this case, we have everything that we need at this moment. At this moment, we have all what we need at the moment to run the calculation for asymmetrical faults because we have the equivalent model for the positive sequence, negative sequence, and zero sequence. Now we are ready to start the calculations, to perform the calculation for the three different questions that we got in this problem.